Okay, welcome everybody. Welcome to the attendees of the program that are joining us in the Zoom call. And welcome also to all of you that are connecting to our live stream through YouTube. Thank you for your persistence. We had some technical issues yesterday morning that were solved during lunch. Basically, Zoom started working. But now it seems like we're live and without glitches. If you see any glitches, let us know. This is panel 3 of the 2020 edition of Next Generation Electrochemistry. This is a program that normally runs face-to-face and for a week, but because of the COVID pandemic, we had to cancel our face-to-face program and decided to keep things going for another year through an online program. And instead of running lectures, we're running panels, and I'll get to that in a minute. This program is funded by the National Science Foundation. They've been funding us since 2016 very generously. ECS is sponsoring us, and you've probably seen, you follow ECS on Twitter or on LinkedIn, that they've been promoting the program, and we're very thankful for that and their support. And it's administered by the University of Illinois Chicago. My name is Jordi Cabana, and I'm in chemistry at UIC. Thomas, who's also in this call, is our administrator. He's the one that makes everything happen. And then we also have George Crabtree, who's our supporting director, who's also at, all of us are at UIC. So, like I said, we've had a condensed version of NGenE in 2020 because of the fact that we had to cancel our physical program. We ran 2 panels yesterday. Panel 2 is in our YouTube channel. The recording is there. Panel 1 couldn't be live streamed, but there's a recording that will go on YouTube soon. And today we're doing panel 3, which is this one, Frontiers in Electrochemistry at the Water Energy Nexus. And this afternoon we'll have one last panel on organic electrochemistry. If you're in the Zoom call and you don't have the information for panel 4, please contact Thomas and he'll send you the link. This is for people that were invited to attend through the Zoom. The idea with these panels is to have a relatively informal discussion that is driven by the panelists. These are people with a very prominent profile in the topic that we're covering. So they're basically the experts, the go-to people. They're going to give a 5-minute opening statement on their perspective of what fundamental questions related in this case to questions of water energy at the water energy nexus exist that have to do with electrochemistry itself. And we're going to try to focus on things that are fundamental more than things that have to do with making money out of this technology. After the 5-minute opening statement, we'll have discussion. The discussion is still driven by the panelists, but we have a group of 40 students and postdocs roughly attending the call. And they have the opportunity to basically connect to the panelists and ask questions as we go. We're live streaming, and it seems like we still are live streaming. And we're going to run for about 90 minutes. We have a 9 and 90 minutes, but yesterday we ran a little over. We will, you know, as a moderator, I'll see where we are, and if we need a few extra minutes, we can see if the panelists can stay. For the panelists, or what we call the NGenE faculty, the most important thing to accomplish here is to try not to dwell too much on the past and really talk about what are the frontiers in the topic that we're discussing. We want to know what we would like to be able to do and we can do today more than what has already been done. It's okay to be controversial. We had controversial statements in both panels yesterday. As long as it's collegiate, controversy is always good. So don't be shy about throwing ideas that you know other panelists might not agree with. This is an opportunity to connect to a group of people that is much greater than your group. So it's your way to intellectually influence the next generation of people that, you know, let's face it, they'll be the ones replacing us at one point. Share your wisdom about how you go about assessing or critically assessing the research that you do and in relationship with the key questions. And let's try to talk as much as we can about electrochemistry and basic challenges with electrochemistry that are really impeding the progress that you would like to get to. For those of you that are attending the Zoom call, you've seen this already. I just want to remind you, we want you to get involved. There was quite a bit of involvement yesterday, and I want you to still not be shy about throwing questions. Yesterday, we couldn't get to absolutely all of them, and I apologize to those that I couldn't cover, but we got through a lot of them, and the panels ended up being very driven by your questions. So we want you to be proactive. Your mics are disabled, so you won't be able to just throw a question. Put the question on the chat. Use the chat feature. Some of you were using the Q&A feature yesterday, so I was going back and forth between the two. It's easier to have them in one place, so see if you can put them on the chat. We'll give you the floor to ask in person, and you can start posting questions the moment the opening statements end, or even during the opening statements, and I'll see when they fit the best. If your mic is not working when we give you the floor, we'll give you a few seconds to figure out if you can fix it. Otherwise, one thing that we did yesterday is that I ended up having to read a couple of questions because the mic just wasn't working for the people that were trying to ask. Don't be afraid to ask difficult questions to challenge the faculty. You want to know what they don't know, and they're going to tell you. They're going to be very frank about it, but there may be aspects that you want to uncover with your questions, and that happened again yesterday. Try to observe as much as you can, and try to use this as a springboard to see how it fits with your career plans. I joked yesterday that perhaps this will make you realize that you really don't want to do a career in electrochemistry. Hopefully it's the other way around, and you see just how much growth is still left in electrochemistry and electrochemical engineering broadly, and that this gives you ideas of things that you can pursue in the future. With that, I'll stop my sharing, and we agreed on an order before we started, and we decided that Brian Chaplin is going to go first. Brian is also at USC, but he's in chemical engineering. Jelena Radjenovic is at ICRA in Spain. So the beauty of doing an online event is that we have the luxury of having people that are international, which we wouldn't be able to do in our physical program. Then we'll have Douglas Cole, who is at NC State. And then lastly, but not leastly, I guess I should say, David Jassby from UCLA. So that's going to be the order of presentations. So Brian, go ahead and take it on.
Okay, thank you. Give me a moment here. Okay, so I assume everyone sees my screen fine? Okay, so yeah, thank you very much, Jordi.
We're not seeing the shared yet.
You're not seeing this shared screen? Okay, is that working?
Yeah, we're good.
Yeah, I have too many screens here in my office. Okay, all right, thank you, Jordi. Thanks for inviting me and thanks for hosting it. As Jordi said, I'm Brian Chaplin from UIC in chemical engineering. I'd just like to begin by giving a brief overview of the reasons that I became interested in electrochemical water treatment, and then also highlight my primary research focuses within this field. I guess to give you a little background, I started working in electrochemistry in 2008 during my postdoc studies at the University of Arizona, where I worked with Jim Farrell. And at that time, electrochemical water treatment was well outside of the mainstream. It still is, but at that time it was well outside the mainstream. However, I was particularly drawn to the topic, I think because of the uniqueness that it brought to the field. And so, for example, I was able to utilize concepts and materials from the field of electrochemistry and then bring them into water treatment. And I think this really gave me a unique perspective that maybe others didn't have that were working in water treatment. So for example, the idea of modulating the potential on an electrode to control water chemistry was very appealing to me, and it made a lot of intuitive sense. Why do we add chemicals to water when we can create them in situ? So that really was something that really inspired me. And at the time, I really thought that electrochemistry was the future of water treatment. In many ways, I still do, although the more you know about things, the more you also see the challenges, which we'll, I'm sure, talk in detail today. And so I've spent the last 12 years or so studying electrochemistry and trying to push electrochemical water treatment technologies forward. Specific focuses of my research group include studying electrochemical oxidation and reduction pathways of priority water contaminants. What I'm probably best known for is the work that we've done in our group of developing multifunctional reactive electrochemical membranes. And so this is a technology where we impart reactivity to traditional microfiltration and ultrafiltration membranes to make them multifunctional and do more than just physical separations. And in addition, we've also done some work in our group on sensor development for water contaminants. And so I want to give a little background on electrochemical water treatment. I know the audience is diverse here, and not everyone is working in electrochemical water treatment, or maybe very few of you are. So my background is brief, and it's more or less summarized in the figure that I'm showing here. This is by no means comprehensive of the technologies that electrochemical water treatment are utilizing, but I think it does cover some of the more popular ones that are being researched right now. So as you can see, I've shown several electrochemical cells here, and electrochemical cells are capable of removing a wide range of water contaminants. So we can have oxidation of a contaminant by injection of an electron into an anode. We can reverse that process and have electrochemical reduction. We can also have electrodeionization of salts, shown here. This is a non-Faraday process. And we can also inactivate viruses and bacteria through reactions with water to form hydroxyl radicals, or we can actually produce disinfectants such as chlorine right at the anode surface. And also there are several ways that we can remove toxic heavy metals, which are shown in the last three panels. We can do electrodeposition. We can do what's known as electrocoagulation, where we have an aluminum anode that produces aluminum ions that then complex with metals. And then lastly, we can do electrosorption. So these are a summary of some of the areas that a lot of us are working in. But of course, there are lots of challenges that need to be overcome. And so I've listed several of the challenges here. First and foremost, we'd like to make these technologies energy efficient, but not only energy efficient, but we have the capability and the opportunity to recover some of the energy from these processes. So for example, we can reduce CO2 on a cathode at the same time we're maybe oxidizing a contaminant on the anode. We can reduce that CO2 to useful fuels. We can also form hydrogen on the cathode that can be used as a fuel source. And there are ways such as using electrodeionization. This is basically like a double layer capacitor, where we can recover some of the energy during the regeneration step. Another need for future research is in the area of selectivity. So I've drawn all these figures very nicely showing very specific pathways that occur. But of course, selectivity is a huge issue in oxidation and reduction, as well as electrosorption and electrodeionization. So this is really a topic that I hope we get more into, because I think it presents one of the main challenges that we're trying to face. I've also shown all of these electrodes as very flat plate electrodes, and that is the case with many electrodes. And one of the limitations is a lot of electrodes have very low electroactive surface area. So there needs to be more work in trying to increase the electroactive surface area. And once we get these high electroactive surface area materials, we have to work on getting mass to them, getting our contaminants to there. So there has to be a lot of work in enhancing mass transport to the electrodes. And then lastly, related to materials, we need more stable materials, especially during anodic treatment, because these can degrade over time, which will greatly increase the costs of electrochemical technologies. And in water treatment, we are working on the cheap. We really have to be able to purify water at very low costs. And so, really working with earth-abundant materials, and avoiding the use of non-precious metal materials is really paramount to developing cost-effective technologies. So with that, I'll turn it over to the other panelists, please.
Thank you, Brian.
Thank you. Let me stop my share.
Jelena, you want to take it on?
Okay, just one sec. So, can you see this properly? Yeah?
No, not yet.
Not yet.
Well, it takes some time to get from Europe, not US. It says that it's screen share, but
Hit the share.
I am sharing. No? It's not getting there?
No, not yet. It's funny, these worked just 10 minutes ago.
Exactly. Okay, I'll stop sharing and do it again.
Yeah, no, it's coming, it's coming.
It's coming now, yeah.
It's just a delay.
Too late, I stopped it. Now? Okay. Just let me know when it's there.
Yeah, the photons move slow across the border, I guess.
Does it have the right visa?
No, I don't know. It's Serbian, so. No, not yet.
No, it's still stuck on that screen that said it started.
If it doesn't work, I'll just talk. It's fine. I mean,
you can also, if you want, you can also send it to me via email, and I can try to share it myself, and you can tell me what slides to put
sure.
up.
Okay, well, there are 2 slides.
It's up to you.
Want me to go next instead?
Yeah, sure. Go ahead.
Or Doug? It doesn't matter.
Doesn't matter.
Yeah, you want to go ahead, Doug, and Jelena, you can try sending the
I'm sending
slides, and we can try to put them up.
Okay, I'll give it a shot.
Yeah, all of a sudden, Jelena, you look like your connectivity is betraying you.
Really?
Send it to me by email, and I'll put it up for you after Doug.
Okay.
How's it look?
Good.
Yeah, you're up.
All right. Okay, thanks, Jordi, and thanks for organizing the panel and inviting me to participate. I'm going to start with just a high-level overview of some of the things that we do in my group, and then talk about some of the challenges that I see in using electrochemistry in the water energy nexus. So as Jordi mentioned in the intro, my name is Doug Call. I'm an assistant professor at NC State, the Department of Civil Construction Environmental Engineering. My group, we focus on a diverse group of electrochemical systems, biological, electrochemical, and hybrid bioelectrochemical systems. We work in the area of water treatment and wastewater as well. And then we also have some work on resource recovery using electrochemical systems, which I'll touch on a little bit. Some projects that we have going on, Brian mentioned electroabsorption. This is something that our group works in particular, electroabsorption of aqueous contaminants, such as per and polyfluoroalkyl substances, such as PFAS, salts. So, for example, using capacitive deionization to remove salt ions from brackish water as a way to desalinate water. But we also look at new ways to use electrochemistry to work with microbes for treatment. So for example, we do a good bit of work looking at electron conduction through electrically conductive materials and how those processes can be used to improve or enhance reactions that we want, for example, during wastewater treatment, to degrade organics and generate gases like methane. And then we also are looking not only at resource recovery, but we're also interested in resource generation, taking a lot of the tools we've learned from bioelectrochemistry and, for example, seeing how we can electrically drive microorganisms to simultaneously treat wastewater, but then also generate new resources for us. For example, converting nitrogen gas in the air into ammonium as a new way to supplement demands for fertilizer. And then the last thing down here is salinity gradient energy. While this isn't necessarily a treatment technology, it's certainly a technology that using electrochemical principles might be able to contribute to our energy needs through the mixing of fresh and saline waters. So it's a pretty diverse set of technologies and areas that we work in. So challenges, so just to build on some things that Brian said, I think, and also after listening to discussions yesterday about batteries and energy storage, I think one of the big challenges that we face is our electrolyte. If you think about water and wastewater, it's a very challenging electrolyte. It's not like a battery. It's not like a lithium ion battery where you have a very precisely controlled electrolyte. You can tune the conductivity. So one of the biggest challenges in our field is how do we overcome the inherent dilute and variable nature of water and wastewater. We also, in these systems, see a lot of parasitic losses. And so what I mean by this is an example is during electroabsorption, we typically see Faradaic reactions, which we don't want to see. And a lot of these are driven, for example, by things that are coming in the water. So oxygen, that has a detrimental impact when we're trying to capacitively store ions in electrodes. How do we improve kinetics while maintaining reaction specificity? Well, if we're talking about a water or wastewater treatment plant, they have design criteria in mind for how long they want retention times, whether it's a hydraulic retention time. And so sometimes the electrochemical reactions might not be fast enough so that when we talk to a water wastewater treatment plant, we can say, yeah, we can meet that 1 hour or 5 hour HRT. So how do we improve kinetics but still maintain the reaction specificity? When it comes to the microbial side of the story, there's a lot of really neat reactions that people have proposed for microbes to do. And I think there's a lot of promise there. But this is where one of the challenges is we have to start crossing disciplines such as molecular biology. We have to understand if microbes are a catalyst, for example, how are they regulating themselves? And what we've seen is that different electrical voltages really change the way that these microbes react to the kinds of pathways that we're trying to drive. From a practical sense, this is a big one, I think, is determining how matrix components affect specificity. Like I said, the electrolyte is highly variable. There's other ions, natural organic matter, changes in alkalinity. And this can all change if you look at for example, a wastewater plant. In the morning, everyone gets up, flushes the toilet, you get your big ammonia spike. How does that impact when we're trying to drive a specific reaction? Scalability, this is always a good practical question. Should we be talking about these technologies for a utility scale? So a several million gallon per day plant, or should we be talking about these technologies for a point of use scale? It's an important question. And I think what Brian was saying, cost is a big issue, and maybe that is a driver of this. And then the last thing, resource recovery. I open this as a discussion point. Resource recovery with electrochemical technologies is pretty promising, but I think we need to think about making sure that the resource recovery that we're targeting agrees with the resource demand. For example, technologies that can make additional methane, is that practical in the sense that it's a valuable resource, or is now, for example, natural gas prices are so low that that resource really is in high demand? And I'll leave it at that.
All right. Okay, Jelena, let's try it.
Let's try.
I am going to put your slides up, and because it's only 2 slides, you can just tell me when to go to the next slide. And
Yeah, sure. I'll tell you. So
okay, so it should be up.
in presentation mode. Yeah, okay, thanks. Thank you very much, Jordi, for inviting me and for putting my slides. So my name is Jelena Radjenovic. I'm working at the Catalan Institute for Water Research in Spain. And it's a pleasure to be here. It's a new experience for me, so let's see how this goes. Basically, I'm starting with a little bit more critical point of view. Not that I'm not a big believer in electrochemical systems, I really am, and I think the future is going to be electrified in many ways. But there are some challenges that I think we as a responsible scientists have to admit and try to resolve if we want this technology to move from lab scale and benchtop experiments to something that is really happening in real life. So there are some technical and operational challenges that are important, and I just wrote here 2 very general ones. So the first one would be that, of course, like mentioned already, current and conversion efficiency for the degradation of in this case, trace contaminants. This is something that we're looking at a lot. So different pollutants of anthropogenic origin in water. This is typically very low, and definitely the way to move towards enhancing this current and conversion efficiency is to look at 3-dimensional materials, porous structures. So typical conventional electrochemical reactor is something that has first been used in the chloralkali industry. This is a plate and frame reactor. I don't think that we can rely much on something like that if we really want to see these systems really applied for water treatment, not just chlorine generation and disinfection. So the way to go there would be, apart from developing new electrode materials, to also look at different reactor geometries. So I just included here one that I always found interesting. We don't use it in our lab yet, but I found it very similar, for example, to what you would have in an RO module, a Swiss roll, so-called Swiss roll reactor. And then another challenge would be, of course, formation of byproducts. I don't have such a great scientific argument like Brian for getting involved with electrochemistry, because I basically ended up by accident doing what I'm doing now. And I'm doing that for the past 10 years, so it must mean I really like it. But the first study I ever published was basically showing that the toxicity of the water that I was treating was increased 250 times. And this is something that surprisingly, by that point, I did not find in literature. So there were tons of papers that were completely overlooking this aspect, like it doesn't exist. So every time when there is chloride present in significant concentrations for every single commercial electrode material, there is going to be a big challenge of formation of chlorate and perchlorate, also halogenated organics. And to deal with that, you would need to have a really efficient post-treatment option, which I don't really know. It would have to be a combination of post-treatment options, really. So I think this is something that people need to have in mind, especially when considering coupling electrochemistry with different pre-concentration technologies. So besides these technical and operational challenges, so state-of-the-art challenges from my perspective would be some that I already mentioned. Well, here is listed as actually number 3, that chloride impact is not really considered in formation of toxic byproducts. Besides that, a lot of studies is done under really idealized conditions, so high supporting electrolyte conductivity, high initial contaminant concentration, if we work like that, it's very, very difficult to extrapolate the obtained data to any real case scenario. Wastewater has conductivity of 2 millisiemens per centimeter, typically, or around that value. That means that you need to use 10, 15 millimolar buffer, for example, solution. All of that, I think, should be changed, really, in literature and improved. Many people are now reporting also new electrode materials, and one of my biggest disappointments after we ventured really in the field of material science is that many of these materials are not properly evaluated. I think there needs to be some kind of an accelerated service life test or similar conducted that accompanies each of these studies, something that gives some kind of information about the electrostability, physical-chemical properties, structure, and so on. I think this needs to be more comprehensively reported. And there is also very limited information on the treatment of real contaminated water. Of course, you can't study the impact of different parameters, ions, and so on using real water. But I think it's necessary to at least try to deal with something more complex. And Jordi, if you want, next slide. Thank you. So what would be the future research directions from my perspective? It's definitely one of the obstacles for a wider scale adoption of electrochemical water treatment, from my perspective, is lack of suitable materials. And I think any research in this direction is very welcome. And we can actually learn a lot from other fields, especially the energy field. There were some presentations yesterday. So we cannot extrapolate everything, but some things we can actually try to adapt to what we're doing. So from my perspective, it always has to involve materials that are not noble, something that is low cost, and not only in terms of the materials that it uses, but also in the synthesis process. Like, this is one of the main limitations why commercial BDD electrodes are not more applied, because they are made by a chemical vapor deposition. This can be manganese-based electrodes. I listed here more or less also things that we are doing in my group. So manganese-based electrodes, nanotube-array electrodes. We work a lot with graphene-based materials, and I think there's a lot of potential for other non-expensive 2D materials. Another thing that I see happening is resource recovery. So recovery of nutrients, metals, of course, as Doug said, it has to be a resource that is worth recovering, right? I guess typical energy recovery that people were exploiting also until now would be the hydrogen production in the cathode. There are also other options. And this can also be coupled with the production of value-added products like, typical chemicals used a lot at industrial scale, like caustic, hydrochloric acid. Also, some people use it for electrosynthesis of different organics. And of course, desalination at small scale. I find this very competitive with RO. We don't work with that technology, but I think this is also an important future direction for let's say, electrochemical water treatment systems. And I think that we will see a lot of work done with hybridization of electrochemical systems with different technologies, whether this is membrane technologies like reduction of folding of membranes, different absorption technologies, ion exchange, and so on. So here I just included a little bit of self-promotion. So we are currently in the middle of a very large project. It's a European ERC starting grant. It's analog to NSF career grants, kind of. And in the scope of this project, basically, we are trying to develop new materials. We are focused a lot on graphene sponge electrodes, doped with 2D materials and atomic doped. But we're also diversifying a little bit and working with other types of materials like titanium dioxide nanotube arrays and different metal oxide coatings. Our focus is very much on organic contaminants, of course, PFAS. And then also other contaminants known to be resistant to oxidation, microbial indicators, and inorganic contaminants. So this is basically a project that when we started it, I thought it was all going to be nice and easy to adopt these materials that everybody seemed to develop with a lot of with no difficulties in the energy field, at least it seems so, but it's actually, there's more to it. So it's a very difficult, I think, thing to adapt a new material to water treatment, because you have multiple factors to consider, which is price, also the stability, that it does not release anything toxic, and so on. So I think here I gave enough to just start a little bit the discussion, if you agree, Jordi. I don't know how long it took me, but I will stop here.
Sounds good. Thanks, Jelena. Okay, so David, you want to take it on? We'll have the last opening statement and then we'll discuss.
Sure. All right. Is it working?
Yep.
Okay, wonderful. So hi, good morning, everybody. I'm David Jassby. I'm an associate professor in the Civil and Environmental Engineering Department at UCLA. Thanks, Jordi and Brian, for putting this together and inviting me. It's a great pleasure to be talking to you all this morning. So just, I don't want to belabor a lot of the points that were raised by the other panelists, so I'm just going to try to keep it brief. Our approach is a little bit different, maybe. We focus primarily on membrane separations. And when I was a graduate student, I started getting interested in this idea of combining membrane separation with electrochemistry, which at the time, there weren't very many people working on this at all. And the idea was to transform a membrane from sort of this passive material that just kind of sits there and doesn't really do anything with the water, doesn't interact with the water, to something that's actually reactive. And my idea, the way to do that is to basically coat the membrane, or to make a composite material that will conduct electricity, and thereby we can now deliver electrons directly to that membrane water interface and start changing the near membrane / electrode environment. We can start doing interesting electrochemical reactions and all the different things that the other panelists have discussed. So over the years, me and my group have developed a range of materials that sort of meet those parameters, and they follow the traditional water treatment sort of membrane. So we do everything from reverse osmosis membrane, nanofiltration membrane for desalination and water softening, and then all the way to ultrafiltration, microfiltration to remove things like viruses or bacteria, or pre-treatment for desalination. We also do quite a bit of work on thermal desalination technologies like membrane distillation. And those are really used to treat high salinity brines. So taking things almost to crystallization, to zero liquid discharge. And again, the overriding sort of methodology and idea here is to be able to deliver energy, in this case electrical energy, electrons, directly to that membrane water interface. And you can really do a lot of cool things. The kind of material that we work with are strictly carbon-based. We do some carbon metal composites as well, but for the most part, these are carbon nanotube-based polymer composites, where we use the polymer to cross-link the carbon nanotubes. The carbon nanotubes give us electrical conductivity. The polymers give us the selectivity. So if we want to make a desalination membrane, we will use something like a polyamide, various kinds of polyamide polymers to cross-link the carbon nanotubes. If we want to do an ultrafiltration membrane, more porous, we will use something like polyvinyl alcohol or something like that. So there's a lot of polymer chemistry involved in the formation of these materials. And we use these materials also for resource extraction and for anything from nutrients from wastewater like ammonia and phosphate through the rare earth elements. CO2 now, I think, could be fairly considered as a resource, particularly if there's a price on carbon. You can now think about mining CO2 from water because there is a value to it. And I think that has a lot of potential, a lot of potential applications for this sort of water energy nexus, because that initial separation is already done for you, because basically CO2 dissolves in water and most gases don't. So you have that initial demixing of your gas stream happening in water. So there's some opportunities there. The other thing that I do quite a bit is I think about the economics of these electrochemical processes. And I do think that working at that water energy nexus or interface, we really have to keep economics at the forefront of our minds. The reason why I say this is because water is inherently nearly worthless. Because, and when I say that is because if you consider the price of desalinated seawater, which is considered the most expensive water out there, right? It's only about 50 cents a cubic meter, right? So it's 50 cents a ton. Give me an example of another commodity material that is that cheap. And that's the most expensive water. If you're talking about groundwater or river water, it's, it's maybe 15, 20 cents a cubic meter. So any kind of solution that anybody proposes for this kind of water has to be very price conscious. And it's part of the reason why it's so difficult to move from the lab to an actual application, is that when you start, penciling out the economics, it very, very quickly falls apart. So you have to think about that, going into these, any kind of these projects. Looking into the future, I'm not going to talk about better electrode materials. Yes, we need them, absolutely. I think there's a lot of opportunity still in using electrochemistry to enhance various separation processes. I think one of the most interesting ones, and I think potentially impactful ones, is to use electrochemistry to increase the selectivity of various membrane separation processes. And really what I'm talking about is to break that permeability selectivity trade-off. So most membranes, if you want to make them more selective, you also make them less permeable, because you basically have to use a denser polymer. So that has implications down the line for the capital expenses when you try to build this out. Can use electrochemistry to enhance the selectivity without changing the permeability of your underlying material. I think there's a lot of opportunities there. There's a lot of opportunities also to make the membranes selective towards things that are not currently being rejected and which are really problematic in wastewater recycling, which is I would say one of the more cutting edge ideas out there, is basically taking, people have been talking about this for decades, taking wastewater and converting it to drinking water. And one of the big problems there is getting rid of these very small polar but non-charged species like 1,4-dioxane or various pharmaceuticals, things like that. They'll just go right through our current treatment process. And can we do something with electrochemistry without breaking the bank to remove them? Membrane fouling also, always a big problem pretty much in every membrane process. We've done a lot of work on that over the years. How can we take advantage of electrochemistry to solve some of these issues? And one area I think is completely unexplored is what happens in the gas phase. How can we enhance gas separations, membrane-based gas separation, using electric fields or electrochemistry or anything like that? There's very, very little work out there. The work that has been done is decades old at this point. And there's some really interesting things that we're seeing there in that space. And I think that's an area that's really ripe for some discovery. Some other areas that are interesting to me are things like AC electrocatalysis. Does it have a place in water treatment? Can we tune the selectivity towards different contaminants or reactions that we want by just tuning the frequency that we apply? And then the other thing where you can use a lot of electrochemistry is actually for process characterization. There's a lot of things that happen. Again, I'm a membrane guy, so at the membrane water interface that are very difficult to probe. And using conventional methods, we don't really know what happens at the membrane surface. But if you have basically a membrane / electrode, you can start probing that very, very small interface. And there's a lot of room for discovery still there. Things like concentration polarization, thermal polarization, membrane fouling. Those are things that you can really probe with very high accuracy using electrochemistry. And then, of course, process scale up, like many people have mentioned already. Most things do die in the lab. And they die in the lab because they're working on the wrong problem. And I say we are working on the wrong problem. We didn't talk to industry to find out what they really need, or it's just too expensive. And we have to think about that because this water energy nexus is a little bit of an applied field. I think it's important to always keep those scale up questions in mind, even from the beginning, from the ground up. That's it. That's all I got.
Okay, thank you, David. So this concludes the opening statements, and we are going to start the discussion. And as it happened yesterday, there is a question from one of the attendees that touches on something that has pretty much appeared in all of the discussions or in all of the presentations, which is the topic of selectivity, which seems to be a biggie in this area. Aditya was asking if, I'm paraphrasing, if the idea of selectivity could be achieved by more than one material, meaning, you could have a catalyst that, or something on your electrode that allows you to get selectivity, but then to David's point just now, also use a membrane that allows you to, clean things up a little bit on the front end before they reach the electrode. Is that something that is being considered? Is it going to be one solution to the selectivity problem? What are your perspectives?
Well, I think I can weigh in on this a bit. So, yeah, selectivity is a very important question. And usually if you look at water treatment, it's going to be a process of like a process train of many technologies, for example. And so you may have to have some technologies up front to remove certain species. So for example, a good one to think about is membrane separations. And membranes are known to foul. So there has to be some pre-treatment beforehand just to prevent the fouling from occurring. Where I mostly am interested in the idea of selectivity is in terms of transformations. And this becomes a very tricky one because you can do these pre-treatments to remove things that are going to foul your electrode. For example, if you have a waste stream, you might have a lot of background organic compounds that you need to remove. And so you can do some pre-treatment to remove those. But ultimately, what we're really worried about in this, at least in electrochemical oxidation of contaminants, and Jelena mentioned this, is the chloride that's present. And so chloride is a very small ion, and it's very difficult to remove chloride. You basically have to do a complete removal of almost everything, like reverse osmosis. And then at that point, perhaps you don't need the electrochemical treatment. So this is really where I've been trying to focus some attention, is how do we prevent the chloride from oxidizing and forming these toxic byproducts. And so it becomes, there are various ways that you can achieve selectivity. You can achieve them based on size, you can achieve them based on charge, and you can achieve them based on hydrophobicity. And so in terms of size, chloride is very small. Mostly it's usually smaller than the contaminant that you want to oxidize. So you don't really have the size option at your disposal. The charge option is not always so great because if you're using an ion exchange membrane, you are basically that's only going to let charged species through. And then the one thing you might have at your disposal is hydrophobicity. So making perhaps very hydrophobic electrodes that are going to react more with organic materials than they're going to react with these ionic species. And so that's one approach, but it becomes very difficult to really get to the level of removal of chloride that you would need to prevent these toxic byproduct formation. So I really think this is, we're supposed to be here talking about challenges for the next generation. And I think this is, really paramount, and at least in the field that I'm working in electrochemical oxidation, because it really can kill a treatment technology that is very useful, very promising at the lab scale. But then when you move up to trying to see, okay, can we actually apply this? You're really faced with this really difficult challenge.
Is this something that membranes could get to, David, or is there no perspective? You talked a lot about membrane and...
I think there can. I think there is. The thing with membranes, I mean, membranes are there to separate things. And you can, I think part of the way maybe perhaps to sort of partially alleviate what Brian was just saying is to concentrate up your solution, basically. So you reduce a lot of the problem with water treatment, ultimately, and I don't care how contaminated we consider our streams are, they're still really dilute. And when you take the funkiest wastewater, it's still, maybe a couple grams per liter. So of stuff other than water, which is nothing compared to like a battery electrolyte or things like that. So one approach that helps with kinetics and reduce those parasitic losses is just concentrate everything up. For example, by using a reverse osmosis process, and then your concentration is much higher. I mean, you can concentrate things up by an order of magnitude or even more using various membrane processes, and then you can hit it with your electrochemical process. But then it just becomes like a waste disposal process, and your volumes are smaller, your concentrations are higher, and the impact of those parasitic losses are perhaps somewhat mitigated. Now, I will say that this is in general in the water treatment field, like dealing with those waste streams that are generated from the various treatment steps that we apply is absolutely critical. And it's something that a lot of people don't really think about, but when you actually look at various treatment processes, and again, desalination is a classic example. Most people think about how much does it cost, or what's the energetic cost, or or the financial cost of treating water. But what they don't understand is buried in that cost is a huge waste disposal component. And this is not really an issue if you're on the coast, because you just put it back into the ocean, assuming you get your proper permits. But if you're inland, there's nowhere to put these highly concentrated brines. And if you're dealing with wastewater recycling, you're going to get high concentration brines that also contain things like pharmaceuticals or personal care products, all these micropollutants that are emerging or have emerged and are problematic, or the various perfluorinated compounds. And having a waste disposal process in there that is capable of degrading a lot of these compounds, I think that's really a niche application for electrochemistry, because ultimately these electrochemical tools, it's a little bit like a sledgehammer, right? You come in there and, well, the way they are right now, they just blast everything apart. And that's really the beauty of electrochemistry, and also the weakness, right? Because you can do chemistry that no other chemistry can do. You can break down these fluorinated compounds. Nothing else can do that really effectively. There certainly is a place for it, but I agree with Brian. There has to be some sort of pre-treatment before. You can't just take your stream and treat it. You probably have to concentrate it up first.
Yeah, another problem is that we're never really seeing the same solution twice. So, water in California versus water in Illinois. And so it makes it very difficult to maybe foresee all the issues that you might have. And one thing I wanted to comment on the selectivity thing is, David was saying about concentrating the waste, which is very important. What we've seen some success in is using nanofiltration membranes that can let the chloride go through, but then kind of capture everything else. So then you get at least rid of some of the chloride, but it's very difficult to get, at least I'm not aware of membranes that allow 100% chloride through and then retain, everything else that you want to actually treat.
How much is too much, right? You're talking about chloride. Chloride seems to be a really bad actor. So what is the tolerance here?
Yeah, well, I would. Oh, sorry, Ryan.
No, go ahead, Jelena.
Yeah, no, I just wanted to add to whole story about pre-concentrating. I mean, it makes a lot of sense because materials tend to perform much better when you have more ionic strength, more conductivity. But what I mentioned before, like for example, my first result that I got, about 250 times higher toxicity, it was precisely on the treatment of reverse osmosis brine. I think it's something that effectively makes it unusable, because if you're going to form tons of chlorinated organics, not just the ones that you can then absorb on granular activated carbon, but also small molecular weight organics, chlorate, perchlorate, especially, then I think this is a big problem. So one way that we have approached this fluoride issue in my group is trying to develop really what Brian mentioned before, more hydrophobic materials, which seems to be working. So I think we will see in the next 5 to 10 years a boom in terms of new electrode materials in this field. So something that was happening in the battery field in the past years, I think water is let's say, I would not say worthless, but I mean,
Of low value.
well, yes.
Very good, very tasty.
Yes, but you know, it's what price do you put a little bit on the issue of PFAS, for example, and the consequences on human health, on environment. I mean, it's true. It's much less supported by the industry. It cannot be compared. The energy field and the water field. We are like hippies compared to the energy field. But I think we just need to have even more scrutiny.
Uh-oh.
Cliffhanger here.
Oh no.
Oh no, did Jelena just break, or was it?
Yeah,
I thought it was me.
just froze up. Yeah,
I think we already had a lot of scrutiny in the field. Sorry.
no, you froze for a bit there.
I froze. Okay.
A dramatic pause. Yes, very dramatic.
Dramatic pause. Okay.
Yeah.
So yeah, no, that's just what I wanted to add in terms of coupling, basically.
We have a question from a student on this topic. He had an idea on chloride, so I'm going to bring him to the floor. Francisco, you're going to be allowed to talk, and you can ask your question directly to the panel. You just have to unmute yourself.
Excellent. Can you hear me?
Yes.
Yes.
Great. Well, first of all, I want to thank all the panelists and the organizers. This is a really interesting opportunity for someone like me to get to know the field a little better. So I'm a fifth year PhD student, and my background is mostly on batteries. But I'm getting the sense from the opening statements that electroabsorption presents some opportunities to isolate charged species. And it seems that chloride is a big problem down the line in the water treatment process. My question is, can you use electroabsorption as a pre-treatment for water streams?
Who wants to take that one?
Yeah, I think Doug could answer this one.
I can answer that. Yes and no. Yes, in the sense that much of the electroabsorption field in the field of capacitive deionization has focused on sodium and chloride as model ions for studying electroabsorption. So we do know a lot about chloride adsorption into porous electrodes. So the most common electrode that's used is activated carbon. Low cost electrode, very high surface area, lots of pores to trap chloride and sodium inside. The challenge is as a pre-treatment to try to remove chloride is you run into issues of all the other stuff that's in water. Activated carbon is used in drinking water treatment plants. And the reason it's used is because a lot of things just naturally adsorb to the surface. That's how we remove those things from water. So for example, natural organic matter, that is going to be coming into the influent of your drinking water plant. So that will naturally want to stick to your activated carbon. And so in the conventional sense of electroabsorption with those kinds of materials, I think it would be pretty challenging. And what we've observed in our research is you can have chloride present, but if you've got another contaminant present as well that naturally physically adsorbs to the activated carbon, then it really reduces chloride's adsorption over time. So there's a lot of competition there. So I think the conventional materials that we use, like activated carbon, might not be the best ones. I think they're going to have to go, back to the first question and be more selective. And how we do that, as Brian mentioned, fine-tuning properties. But then I think, we also need to reach out to chemists, material scientists, those people that are thinking about novel ways to functionalize the materials so that they grab just specific molecules rather than just grabbing everything that's charged. and there's a lot of promising work coming out in those areas. I think as a environmental engineer, we have to work with them to say, let's try to think about this in a, you know, real context, a real water or a scale up or a cost issue. But yeah, so a short summary is, yes, you can remove chloride, but as a pre-treatment, I personally think that that would be kind of challenging with all the other stuff that's going to come in with your water.
So just a follow up to that, to bring it to the, you know, even further into the electrochemistry, you know, the nitty gritty of electrochemistry. You talked about using, you know, basically a capacitive mechanism. And so paraphrasing David, that's also pretty blunt a tool in terms of selectivity. I mean, you just charge the surface of your electrode and whatever's charged attaches to it, right? So is there, you know, a design rule that you could go by that uses a capacitive mechanism but embeds some selectivity? Or are you thinking about, you know, a completely different mechanism? And this is, you know, for everybody, but, you know, you were bringing that up.
Sure, I'll just say a few comments on that. I mean, there's some things you can do to the standard activated carbon electrode. You know, you can tweak the pore sizes, you can tweak the surface charge, and those can all have some effect on, say, whether you're selecting chloride over nitrate in water. But I think, you know, you're still going to have lots of other anions present in a real water. You might have sulfate, for example. Of course, they're varying concentration, and so concentration has an effect as well as when you're trying to separate things. In terms of completely new directions, there are people working on intercalation electrodes. So essentially, take battery electrodes and stick them in water. And they're finding that you can get pretty good selectivity. And so I think, and there are other groups that are now trying to tweak some of the redox properties of those intercalation electrodes so that they can be more selective for even specific contaminants. And that's promising work. I guess, you know, it goes back to the challenges of how do we make that work in a real water environment? Because a lot of the basic work, maybe they use a perchlorate background buffer, or they're operating at a pH of 2 or something like that to show the proof of concept. But how do those, I mean, that's one of the challenges, is how do we find a chemistry that's stable in a water treatment site type setting?
So Doug, so the research that you're mentioning, do they suffer from lower surface areas with these battery electrodes? Because that's primarily why activated carbon's so great, right, for electroabsorption. Yeah,
I mean, there's a big difference in the surface area. You also, sometimes the cyclability, so how many cycles you can run, can be limited in those intercalation electrodes versus the activated carbon. So yeah, there are some limitations. I think what's most promising is it's making us think more about a structure that can allow for selectivity.
Okay.
Yeah, this also connects, you know, you've now connected the issue of efficiency, which Jelena brought up, you know, early on in her opening statement, within the issue that you've all brought up, which is how in the world do you work with real water when your concentrations are so low? So basically your supporting electrolyte is a really bad electrolyte. Is the only option to pre-concentrate, like David was saying, where you almost treat it more like a waste treatment? Or are there other creative solutions to the problem of, you know, coupling efficiency and high current rate so that you can treat water fast with the fact that you have a really lousy electrolyte?
I think the pre-concentration step is a good solution. Another thing might be, you know, not trying to force a square peg into a round hole. So what I mean by that is maybe we're trying to apply electrochemistry to drinking water treatment, and maybe it has some niche applications in that, but maybe it's better to look at industrial water treatment where, you know, the concentrations, the salinity is higher, they have more tolerance for these byproducts that might form. You know, but I mean, it's akin to having it be an offline process, like David mentioned. Like, you know, if it's in drinking water treatment, maybe it has to be offline just to be efficient and also protect against some byproducts that might form. But I think industry is a great place where industry needs to, in many cases, have zero liquid discharge, and so there's a lot of opportunity. And I think a lot of people are trying it in the industry of incorporating electrochemical technologies in order to achieve that zero liquid discharge.
I do want to add
that you can square that circle. Is that what you're trying to?
Well, I mean, that's somewhat, but kind of not trying to say, okay, I'm gonna give you an electrode that you can put on your drinking water, on your tap, on your wellhead. That might not be the right place to focus because of all these challenges. Or maybe it's just me getting older and giving up on the real challenge. But,
don't give up, Brian.
But there may be ways around it, but there also are the lower hanging fruit in some cases that you can attack.
I think one thing that Doug sort of touched on and is, well, one place that maybe requires a little more thought is what electrochemical processes can we achieve below water electrolysis? So what kind of impact can we have using electrochemistry without inducing any kind of electrooxidation or electroreduction? And adsorption is a great example of something like that. But are there other phenomena we can take advantage of in order to achieve things that we can't achieve using standard approaches? So one area that I'm very interested in is nucleation. Nucleation and growth of crystals on surface is a huge problem. Certainly a problem, membrane separation is also a problem in heat exchangers and anything that basically is immersed in a high salinity environment. And we're finding that you can do a lot with very low potentials, actually. You don't even split water, but you can really change the near electrode environment in a way that is very energy efficient and can be highly impactful on your process as well. And that's another area I think that is, has a lot of potential, I think, for the future. And just trying to maybe back away from just explore the entire range of opportunities in the electrochemical space.
Jelena, so what do you think? Should Brian give up? You were saying not to give up?
No,
what is
totally
the opportunity
not.
there?
I don't want low-hanging fruit. No. I mean, in my scientific career, I went through a lot of frustration, I have to say, and especially once we delved into. Can you hear me? Okay, just to see Jordan's face. It's funny. Yes, you can hear me. Yeah.
You see me freezing. I may freeze temporarily. Okay. I have my own issues of connectivity. So
Okay.
Yeah.
So
look at Brian.
especially after starting with the whole adventure of developing new electrode materials and so on, and you realize that there's a lot of papers not being very honest, and you try to reproduce stuff, it's not working in your lab, and so on. I think that we can really put a lot of hopes in this whole set of new materials that are emerging. So in my group, we are working a lot with graphene. When I say graphene, I don't mean the expensive one, okay? I mean reduced graphene oxide, the one that you can produce in an economic way. We work now a lot with 2D materials, but nothing that would be expensive, I don't know, noble metals, nothing like that. So we are getting some promising results in terms of chloride. And I think, like I said before, this path towards maybe more hydrophobic electrodes, maybe that's the easiest way to tune this selectivity for really organics, at least most of the organics, and not so much towards chloride oxidation. I think that, so especially in terms of the whole problematic of PFAS and what people are finding in especially in drinking water in US and Europe, I really think that even for drinking water, there's potential for these systems, because we may not have many other options than to go this way. And just if all the money and all the energy that has been put into the energy research and development of new batteries would have been placed also in water research, maybe we would already be there. So I mean, I can't argument it with really published scientific evidence. We are working on that, but I think there is potential in terms of electrode materials and going towards more porous 3D geometries, something that would be like a filtration unit, filtration device, and moving away from the 2D reactors. And industrial wastewater treatment is, of course, very interesting, easier to do, less stringent parameters for the treated effluent, of course, than for anything else. And this is where electrochemistry has been applied, I guess, since the 70s, 80s. They already started treating textile effluents with electrochemical units and so on. But I think we can do more than that. I think it's kind of our responsibility to try to push forward in this field.
She froze again.
Yeah, she froze again. So I'll finish her statement, but no, I didn't want to. I don't want to put up the sentiment. I didn't want to put forward the sentiment that.
I think we'll have a lot of.
Jelena, you're going to crash us out again here. No, go ahead. Go ahead. Sorry.
I'm not going to talk. It's fine. Just.
No, I just wanted to follow up on that because I wasn't trying to have the sentiment that we shouldn't apply it to water treatment, but that these offline processes at water treatment might be a better option. Because I think we never answered one of Jordy's questions earlier about like how much chloride is too much chloride. And that's a difficult question to answer, but we can say like the byproducts that form from that are being regulated, the ones that are being regulated they're being regulated at micrograms per liter levels. So it doesn't take much to get to 10 microgram per liter levels of these chlorinated compounds. And these are only the ones that are regulated. There's a whole host of other, they're traditionally called disinfection byproducts because they form from adding chlorine to water. And in the case of electrolysis, right, we're forming chlorine, and we're also forming chlorine radicals, and we're forming a whole host of other halogenated species that then react with the organics. So yeah, definitely, I think we can make progress in tailoring electrode materials, but we also have to keep in mind that this ultimately is, if we're focused on water treatment, this is people are going to drink this water, and we have to be very, very thorough and very cautious about, not just monitoring, the 5 regulated HAAs or something like that, but also doing a complete analysis. And Jelena, I know you've done a lot with toxicity testing and things like that, which is probably the right approach, right? Not just monitoring these 5 things are regulated, but how toxic is the water after treatment? If we see a 2,000 times increase, that's bad. It has to be definitely a lot of scrutiny on that side of things. There's a large barrier to get in, I guess.
Jordy, can I add to one comment to that?
Sure.
Yeah. So one thing, and I know Brian probably have maybe more experience with surveying the field. Is I don't think this is a problem that's unique to advanced electrochemical techniques. I've seen byproducts in a lot of advanced technologies that are emerging. So it's not just electrochemistry that suffers from this problem. A lot of other AOPs, advanced oxidation processes, that are many emerging, like plasma treatment of water. There's byproducts that form. It can form N2O gases. There's other advanced techniques out there. And so this isn't isolated just to electrochemistry. And maybe Brian or David, you guys might be more familiar with some of the AOPs that are emerging and have some of these issues as well.
Yeah, I think it's just part and parcel with these, highly reactive systems. They're not necessarily selective. And if you have something in the water, it will transform, and we don't really know where it will transform to. A great example of this is ozone, actually. Ozone treatment has been around for decades, and it's very sensitive to bromide concentrations. If there's any bromide in the water, it's very difficult. You get bromate formation, which is highly carcinogenic. And this is also something we need to be wary of is that as analytical chemistry methods improve, detection limits go down, and new contaminants start become regulated, or their regulation levels drop. So this is something that's going to happen potentially with ozone, because bromate concentrations right now, I think, are 100 ppT, and they're talking about dropping into 10 ppT. And if that's the case, you won't be able to use ozone anymore to treat water, because there's no way that you're going to be able to go below that 10 ppT. Every water has just a tiny bit of bromide in there. So it's inevitable that you're going to exceed the limit. And that's also something you have to be aware of, at least when you're, this is more for the students, when you're thinking about going into this area of water treatment. It's highly regulated, and it's regulated by different agencies. And if you're in Europe and in the US, it's different. If in China and India, it's different. It's all different. Every country has its own standards and its own way of assessing things. And one method that works here may not be applicable somewhere else, just because of the various regulatory burdens that are put in place to protect human health and the environment. So it's also something we have to be very cognizant of. And again, that's also very different than some of the other sort of traditional electrochemistry areas that, nobody cares how a battery works as long as it works. I mean, I'm being facetious here, but there's no, as long as it doesn't catch fire, we're good. That's not the case in water treatment.
We have one last question on the topic of chloride from Grace. So I'm gonna bring her on. She had an idea that she wanted to run by you. So go ahead.
Hi. Yeah, thank you all for organizing this and making us able to still participate here. My name is Grace Lindquist, and I am a second-year graduate student in Shannon Betcher's lab at the University of Oregon. And recently, the topic of chlorine evolution has become sort of a hot topic in water electrolysis, because we're moving toward impure water sources for that. And some of you have spoken a little bit to this. And I recognize that, with water treatment, it's different because there is no reactivity involved and it is more electrosorption based. But one approach has been to use like chloride blocking layers on the electrodes. So like a manganese oxide or a metal oxide to just prevent chlorine from reaching the surface or control and tune pH environment. Have any approaches like this to electrode tuning been used, or are they just too expensive and not really economically justified for water desalination?
So I can comment a little bit on that. I don't know completely the state of literature. I can tell you what we did a little bit in our group. So manganese oxide electrodes, I think in this case, the main issue with them is if you can make them in a way that they're stable at high potentials, because normally to degrade all these contaminants, you need to work at very high potentials. So 3 volts versus standard hydrogen electrodes, for example, to degrade PFAS or more. And that's the challenge, really. So in general, with commercial mixed metal oxide and metal oxide electrodes, this long-term stability is always an issue. But I think this is particularly challenging with manganese. I'm not aware that anybody really managed to do that. I don't know. Please correct me if I'm wrong. To use these electrodes for contaminant removal and avoid chlorine formation.
I've seen most of the work in seawater electrolysis, where it basically is, not that good at chlorine evolution, but much better at oxygen evolution. But kind of, if we're focused on and we've kind of hijacked the conversation to focus only on electrooxidation, but if you're looking at electrooxidation of pollutants, you need electrode, like manganese oxide would not be a good material because it doesn't get to high enough potentials, as Jelena said, to generate, to oxidize PFAS or to generate hydroxyl radicals. So you may have less chlorine evolution, but you probably have poor performance for the electrooxidation of your contaminants. But I mean, that's, those ideas are thinking along the correct lines, right? How do we tune, how do we minimize chlorine evolution and then go through pathways of oxygen evolution or other pathways that we prefer.
So we're introducing the topic of materials now. Erin had a very broad question on this topic, so I'm gonna give her the floor and have her ask her question.
Awesome. Thank you, Jordy, and thanks for everyone for organizing. My name's Erin Gaffney. I'm a third-year graduate student from the University of Utah in the group of Shelley Menchier. And I just had a question. So in this field, we have so much opportunity to draw from other fields, especially in the topic of electrode material and design. So my question is, how do you make your research hypothesis driven and systematic in your research design and electrode design instead of just using a trial and error approach?
Mm-hmm. Yeah, good question.
That's a great question.
Yeah, and that's, you've kind of nailed it right there. That's been the general approach, is trial and error and borrowing from other fields. I think there is an opportunity for a bottom-up approach. You know, we're working on this, but it's very early, and I'm sure, you know, a lot of people are working on this approach. But basically, if you can utilize things like DFT studies and machine learning algorithms, you can start to see, you know, you can start to develop molecular descriptors for different materials, and then see correlations, you know, and with things that you know that work well. You can see correlations between the materials that work well and then new materials that you're designing, for example, on the computer. And so we're trying to get into that area of this bottom-up approach where we, you know, have some materials that work very well for example, for PFAS oxidation, and then we want to do a scan of, you know, other materials. So we're utilizing the DFT and the machine learning to do a material design. So there's opportunities for that, but, you know, that's a challenging thing. And to date, we don't have any results, but that's possibly one way that you can, you know, look for new materials instead of just going out and trying what someone else tried or what worked in another field.
I think that we're in a somewhat advantageous space because we're a little bit behind some of the work that's been done in some of the energy storage and energy generation fields. And I think that it's pretty, I mean, there's so much literature out there. People have investigated so many different materials for completely different applications. You can kind of, if you do your, you know, your legwork, I think you can narrow down a lot of the potentially attractive materials based on what other people have done already. And the thing that you need to remember with, you know, some of the, you know, things that sort of will constrain your variable space are, you know, the redox, for example, if you're interested in electrooxidation, you know, the redox window that you need to think about, and you can probably find out whether these materials, you know, have been explored or, you know, are stable at these higher, or whatever the window you're interested in. You also have to, this is something that, you know, we've touched on, but I want to emphasize, the scale of water treatment is gigantic, meaning the volumes that need to be treated are huge. Very few industries are at the same scale, maybe the petrochemical industry, but even that's probably not nearly as big. And when you are thinking about, okay, can this process be scalable? Can we use it in, you know, in a real treatment? You're gonna probably be looking at, you know, thousands of square meters of electrode material at the minimum for reasonable, to treat a reasonable amount of water. Just to like get you know, to align your expectations. A reverse osmosis plant, which treats about 20 liters per square meter, okay, will typically have about somewhere in the area of 500,000 square meters of membrane. So if you use sort of a similar, you know, approximation, maybe you'll treat 20 liters per hour on a square meter of electrode, then you're gonna, and these are the scales that you need to think about. So a lot of the materials are just completely eliminated right off the bat, just when you start thinking about how big these things have to be. So there's some ways that we can whittle it down and make a pretty strong hypothesis, I think, just based off what other people have done and the constraints that are inherent in water treatment.
There's a similar question from Federico. I'm gonna give him the floor. Federico, if you're there, you can go ahead and ask because it's connected to what they're discussing.
Hello?
Yeah.
Well, thank you for organizing this event. My question was, do you see any potential applications for 4D materials at the electrode? Now I'm aware that Professor Jassby has just basically shot down any questions regarding scalability, but I was still wondering, if there's any potential application for 4D materials.
Can you elaborate on what you mean by 4D materials, just so that we're all on the same page? Because I wasn't sure what you meant.
Well, I guess in terms of looking at contaminants, species that are at the electrolyte, and basically, that may have some sensing applications in regards to, just general state of the cell.
So the fourth dimension is what? How things change over time, or?
Yeah.
So something that adapts as that changes as it goes. Is that what you mean?
Yes.
I think so. I think that's actually really one of the main attractive features of these electrochemical materials is that they can adapt to the environment, or they can be adapted to the environment by applying an external stimulus. And I really think that that's probably the main selling point of these electrochemical processes, that you can tune them. They can be responsive to the conditions, the local conditions. And I'll take it a step further. If you can sense the local conditions, which you can do using some of these electrochemical analysis methods, you can then modify your process on the go. And that's very different than what currently is done in any water treatment process, which is basically, after everything is done, you take a grab sample and you do the analysis. And having these responsive materials that can actually can facilitate self-monitoring, that is very attractive. And I will add another plug for electrochemical sensing. And I know Brian works on this, I work on this. The state of the art in water treatment for sensing a lot of contaminants is absolutely atrocious. We still rely on, it's actually really primitive. I'll say, we can't even measure chlorine and chloramines in real time. That you still have to take a grab sample and take it to the lab. There's no online sensing method that is currently in place. You can do that easily using electrochemical sensing. That's a simple process. It's still not applied, and there's huge room for discovery in that space. And microbial contaminants, that's a big one. Coming up with sensors that are selective towards E. coli or fecal coliforms or viruses. Imagine if we could sense this COVID virus in wastewater just in real time. We could have an early warning system for the emergence of the hotspots. That's a great way of monitoring the presence of the virus. But right now, how do we do it? We take a grab sample, we go back to the lab, we have to do some sort of the DNA analysis or anything like that. So yes, the emphatic yes, there's a huge space for these 4D materials. You just have to make them cheap or find the right application.
And one thing just to add to David's comment about scale, and I think one question, and I raised this in my slide, was I think we naturally think of applying these technologies to a full-scale treatment plant, but are there other scales where we could use maybe a more expensive technology or electrode? So, point of use, there's a growing interest in point of use systems, in particular here in North Carolina, because we have really bad PFAS problems in water. So even the most advanced drinking water treatment plants are struggling to remove PFAS. So now people are starting to bring up the discussion of, can we do this with a point of use system instead? Much smaller scale. And those systems, whole house filtration systems can get pretty expensive. Now, you know, does it mean that we can throw in a expensive 40 electrode in there and that people would still buy it? Or what does it mean for people that can't afford a system like that as well? So there's a lot of questions there, but I think the issue of scale is an important one, and that'll play a role in where maybe some of the more expensive electrodes and materials can be used.
So we're technically 5 minutes over. If you have 5 minutes, we'll do one last changing gears. This question is a question that we've been posing to every panel, and it's by Mike. And I think that it's a good idea to put it on the floor now. It has nothing to do with research, and it has to do more with electrochemical education in the context of your topics. So Mike, take it on.
Hello? Can you hear me?
Yep.
Okay, great. So my name is Mike Gerhardt. I'm a postdoc at Lawrence Berkeley National Lab. And the question I've been asking to kind of all the panelists is how can we improve the teaching of electrochemistry today? So like one of the ideas that's been thrown around is maybe we need a new book. What I'm curious also to know is whether electrochemistry should be confined to specific departments, or should it be you know, coalesced into its own sort of field or department. But I guess do you have any comments on that, or what else would you do to try to improve the teaching of electrochemistry today?
Yeah, good question. I mean, as you might be able to see right here, I've positioned the Bard and Faulkner behind me for this panel, but I teach electrochemistry. I'm in the chemical engineering department, and I'm, you know, I like the current text, Bard and Faulkner, as, you know, a guide in terms of introducing students to electrochemistry, and then I can kind of add my own flavor there. And I'd like to hear from the other panelists too, because being in the chemical engineering department, it's much easier to offer an electrochemistry class. There's lots of people doing research in batteries and things like that, and so I kind of, you know, I'm able to kind of sneak in my topics on water treatment, and you know, I find that the Bard and Faulkner is a good intro to, you know, a general audience. You know, I think it's, I'm not so sure it's that having its own department is necessarily the way to go. Maybe in certain areas, but I think it's good for more diverse departments in the sciences and engineering to offer their own version of electrochemistry, and you know, in terms of, and that'll allow, you know, laying down a framework for, you know, the basics of electrochemistry, because electrochemistry seems very simple at the beginning, and then the more and more you get into it, you see the complexity. But every department and every field that's using electrochemistry might have their own angle on it. And so, you know, what I'm teaching in the chemical engineering department might not be exactly what I would teach if I was in environmental engineering department. And when Jordy teaches electrochemistry, he might, in his chemistry department, he may have a different focus. So I think it's important to, you know, maybe fine tune the material for the audience that it's for.
I can say I teach a electrochemistry component in a graduate class that I teach. It's very basic, just gives the just basic principles. I force all my students to take an electrochemistry class in the chemical engineering department, and they complain about it because I think they don't really see the relevance to the work that they do, because a lot of it is based on energy storage. Actually, that's what they're focused on, and not necessarily on not on a galvanic cell. So they focus on the opposite side of things. It would be nice to have a dedicated electrochemistry class, I think, in the civil engineering department. I think you'd actually have a lot of buy-in from students. It's certainly something that is worth thinking about?
Yeah, I think it's important to teach the fundamentals, because from my class, I get a lot of people from who are doing energy storage, and they actually complain that I don't talk enough about how a battery works. But kind of I focus more on the fundamentals and then say, okay, whatever your research area is, you should be able to take what you've learned, you know, in this class, the fundamentals, and apply it to your specific field. I think that, you know, there is some merit to their complaints, is that it's not always easy for students just to take the basic fundamentals and apply it to their field. And so that's why, you know, if electrochemistry is offered in more settings, you know, the fundamentals can be taught, and then examples of how this applies to batteries, or how this applies to electrolytic cells and sensors and so forth. You know, then the instructor has the opportunity to go into detail on those things. And that really is, I think, needed for students to kind of make the connections between, these are the fundamentals, this is how I apply the fundamentals to my specific field.
So this came up yesterday, and the panelists, you know, some of them were energy storage people, especially in the morning. And they actually said that the current textbook doesn't quite align well with what you would want from, you know, from an energy storage perspective. So what I'm hearing is that the current textbooks are not quite aligned with the things that are important to you when you do your research. Is there a particular aspect that you think is missing in current textbooks that would be very useful for people to understand in the context of, you know, applying electrochemistry to all of these wealth of water processes?
I guess I'd bring a lot of outside material in. So I guess just in terms of, you know, the class that I teach focuses a lot on methods, because I find that a lot of students who are even working in electrochemistry don't have a clear understanding of the methods. So I would say that there maybe has to be more than one electrochemistry class. I mean, there has to be one just getting students up and running on what the methods are, what are they actually, you know, what is a CV actually, what's actually happening when they're doing a CV scan. You know, and yeah, I guess there are, in terms of water treatment, there isn't really, to my knowledge, a textbook that focuses on electrochemical water treatment. And so then I'm able to bring in my own research and things to that, which, you know, I think is, I don't know if there necessarily needs to be a new textbook. Maybe in batteries, there's been a lot more done, and maybe some revising of a textbook for energy storage is needed. But I find it pretty easy to bring in, you know, my own knowledge and expertise in the field and kind of complement the fundamentals.
Yeah, I'll give you an example of what they were complaining about. One of the big complaints with Bart and Faulkner, and I've heard this complaint before, is that it's very much focused on classical electrochemistry, which has, first of all, a molecular component, and second, it's focused on the redox in solution processes. Mm-hmm. Whereas a lot of the redox that is interesting now is happening in the solid, right? And you know, Bart and Faulkner is essentially silent on that. So they were complaining that there's not enough of that adaptation to the solid component. I'm hearing that may not be as bad with water, I guess, because you're still doing a lot of processes that happen in solution. So,
yeah, I think it's easier to translate Bart and Faulkner to water treatment because it is basically solution based. You know, it's an ideal electrolyte, so that's where we kind of bring our own expertise in to fill in the gaps. But yeah, in terms of energy storage, I can see that it doesn't really go into the level, really any level of detail in what's going on inside the electrode materials. So I can definitely see that criticism.
Anybody else wants to add anything to that point?
I don't have anything to add about teaching. I'm a little bit worried basically about stimulating the interest in general of students in doing environmental electrochemistry, because it's a field that is subject to so many stringent regulations. I think it's also a source of a lot of frustrations. So that's a little bit, you can't be as creative in electrochemical water treatment, I think, as you can be in, I don't know, adjacent fields of material science. Sensors, you can put a little bit of platinum and and things go smooth, maybe, you know. So that's a little bit, I think it's important to try to not create, so there's already a certain hype in science, but to popularize it and make it seem maybe less scary to students, because I believe most of the students of chemical engineering, for example, or environmental engineering, I don't think they would really maybe necessarily choose electrochemistry. Maybe it just seems something very difficult to do. So yeah, I don't have really anything.
I will say that to make you feel better, you will never put platinum in a battery either, right?
Okay, yeah.
So a lot of these things do actually translate quite well as somebody that works in that field. I just wanted to, I'm not here to give my opinion, but I wanted to make you feel, students that they can feel better, that if they go to batteries, they're gonna have the same problem.
Good.
So Jordi, so since you had a panel on energy storage and they're complaining about the textbook, and presumably you have the experts in energy storage, then you should get that group together to write that textbook, perhaps.
Yeah, so apparently Henry White at Utah is,
okay.
I think, Barton Faulkner, and somebody said yesterday that he is thinking to bring some of those elements in the next editions. Kind of, the tongue-in-cheek comment was that, if polarigraphy or I can't remember what other technique, needs to be explained in this day and age, that is probably, a bad sign, right? So, de-emphasizing some of the things that are there that are really, really classical and bringing in.
Sure. Yeah, I heard there was a new, last time I talked to Al, he said they're writing a new textbook, but I have no idea if that's still going forward. I think
Henry White is the one that's spearheading that. With him.
Okay.
It's a derivation of what his textbook is. So I don't know exactly what the arrangement is, but I had heard that before.
Okay.
I don't know what the timeline is.
Sure.
Yeah. Okay, so it's 11:45, and Jelena is in Spain, and she mentioned that we're probably about to hear fireworks because tonight is a fireworks celebration in Spain. So it's also a very social celebration, even in these times. So I think we're gonna leave it there. I've taken enough of your time. I really, really appreciate that you joined us today, that you gave us, almost 2 hours of your time, because we connected a little early, and that you share your insights with the attendees and with the world. And that you also hung in there with some of the little glitches that we had with Zoom, which seem to be inevitable. Thank you, David, Brian, Jelena, and Doug, in the order that I see you in my screen, for joining us today. Thank you for all the attendees that are still there, and anybody that is watching us on YouTube. And thank you for all of you that are watching after the fact. And we have one more panel at 1 p.m. Everybody's invited to join us. It's in the topic of organic electrochemistry, and I sense that some of the things that have come up here may come up again. And so, so hopefully everybody can make it. Thank you, and see you out in other spaces.
All right, thanks so much, Jordi.
Thank you, Jordi.
Nice seeing everyone.
See you guys.
Bye.
See you, everyone.